very happy to be a part of this seminar and webinar that you guys are hosting, because I've learned a lot from everyone's presentation so far, and hopefully I will contribute back a little bit. Today, I wanted to talk about AC interference analysis, particularly about the workflow with XGS-AFD. And I will apologize in advance because I'm based in North America, so a lot of my units that you'll see are going to be feet and inches, and I am sorry. It's just what we deal with. So in the presentation, what I'll focus on is really what their concerns are related to AC interference studies, or what people really mean when they're talking about AC interference, and try to highlight some of the techniques for performing those types of analyses with XGS-AFD. So at the end of my presentation, it's my hope that you'll be able to describe the physics and concerns of AC interference and what type of hazards can be created from a transmission line next to or near another metallic object, and develop some efficient workflows using XGS-AFD. So to get to that goal, we're first going to make sure everyone's on the same page as far as what AC interference is, the physics associated with that. Then we'll talk about some of the recipients associated with AC interference and what engineers are potentially studying for these effects in shared corridors. Then I'm going to switch over to the software and step through some model development with XGS-AFD and some of the analysis, how you look at the results of that software. So first, let me get into the physics of AC interference and also set my timer so I don't run over. So there's three primary ways that we are coupling from a transmission line to an adjacent metallic object. And the first, most prevalent, is usually an inductive coupling mechanism. So our AC high voltage lines have an AC current that produces a magnetic field, and that magnetic field will produce or induce a opposing current and voltage. So this is one mechanism that we can couple from our transmission line phase conductors to adjacent objects. Another coupling mechanism is called our capacitive coupling mechanism. This is based off of the electric field. So this is going to be dependent upon your voltage level of your transmission line. And it's really dependent on the affected exposure area of the metallic object that you might be coupling to, unlike the induced coupling or inductive coupling mechanism, which is really more for parallel conductors or parallel metallic objects. And then the final coupling mechanism is going to be this conductive coupling mechanism. This is typically associated with the fault conditions of a transmission system. So we can have current that will flow through the tower, through the earth, and conduct directly to a pipeline or some other object. And it doesn't necessarily have to be through the earth, or it can be through some other medium, but conductive coupling is usually associated with fault conditions. Primarily, we're concerned during steady state operation of the induced voltages that could occur, as well as potential capacitive coupling. In steady state operation of our transmission lines, we have balanced magnetic fields. So as illustrated on the right, this is a tower in a delta configuration where we have one phase that's 1,000 amps at 120 degrees, another phase is 1,000 amps at 0 degrees, and a third phase is 1,000 amps at 240 degrees. So that phase separation, vectoral separation, allows for some cancellation to occur. And what we know is as we get those phases closer together, we have greater cancellation and therefore reduces the magnetic field out from our right-of-way. If we look at this, we can have a couple example spacings. So we have one tower where we separate the phases by 20 feet from our two phases on the right. So this would be maybe a 115 kV transmission line. And if we compare that to a 34 kV or 345 kV transmission line, where we have much greater separation from one phase to another, we end up with a greater magnetic field along the right-of-way due to the greater separation from one phase to another. And essentially what we're seeing is that one of our phases that's closest to the Earth is having a greater effect for our magnetic field that could be inducing on nearby metallic objects. So of course, the way that we arrange our phases is going to affect our overall magnetic fields in the right-of-way. So on the left, we have that delta configuration, and that's represented in this chart on the right as our orange line. Here we have the H-frame configuration with the gray line. We see a greater peaks of magnetic fields around or outside of that right-of-way as we have these outer phases having a greater influence. But on the central point or the middle of our right-of-way, all of these phases cancel out their magnetic fields. So we have a reduction in our overall magnetic field there. We already showed the vertical configuration shown here in this yellow line, and then we have a double vertical. So this is where we have two circuits of our transmission line, but if we phase them optimally, meaning that we have phase A, phase B, and phase C, compared to phase A, phase B, and phase C, we can have an overall reduction in our magnetic fields that we would have during steady state conditions. One thing to note is there's often some sort of maintenance process associated with transmission lines. So one of these transmission lines may be out of service or one of the circuits may be out of service on this line, and that can result in a analysis that would initially start out as the double circuit configuration, but then be in a vertical configuration when you have a single outage on your system. And this is all during steady state operation. During a faulted state, what we have is a significant amount of current going through one of our phases, and that results in a much higher magnetic field. So we can show the magnetic field in this gray line during a fault scenario compared to our two previous magnetic field density or magnetic field strength from the 345 and the 115 that we showed earlier. So next I want to get down to the recipients of AC interference so that people are understanding what type of objects we're looking at when they're near transmission lines. And one thing I'll say is I'm going to try and get through this presentation portion of the webinar relatively quickly so that I can get to everything on the XGS Lab software side of things as well. So typical recipients will be other transmission lines and distribution lines. Those are metallic objects that you can induce or couple voltages to. Often AC interference studies are going to focus on other foreign utilities such as pipelines and railroads, as we see illustrated on the right. These are common because they're both long utilities that require a lot of space, and often when you're routing these transmission lines, it can be convenient to route a new transmission line next to an existing railroad or an existing pipeline right-of-way. It just creates this other hazard of AC interference. Other objects that might be considered are cables or vehicles and maybe even buildings and structures, since anything that's really metallic can have some sort of coupling from our transmission lines to those recipient objects. Now I want to go in a little bit of detail about pipelines so that people understand some of the construction of those. Usually when we're thinking about AC interference as it relates to a pipeline, we're concerned about appurtenances. These are locations where there are devices related to that pipeline that may be high touch locations or just locations where equipment has additional sensitivity. So this can be pump stations, test sites, valve locations. We also want to understand the material of the pipeline, its diameter, its thickness of any sort of coating material that you may have on there. Often pipelines have a protective coating to protect them from the soil and corroding in that soil. The challenge is that that coating also allows a voltage to be induced upon it more easily. So that voltage that we'll look at for steady state operation for pipelines typically we have a couple criteria. One is going to be our personal safety. And in North America, those touch voltages during steady state operation are usually limited between 15 to 50 volts, depending on the entity. For the pipeline integrity itself, we're primarily concerned about an AC corrosion phenomenon. This essentially is you have a sufficient enough induced AC current that accelerates the corrosion of the pipeline in any points where you may have any nicks or holes in that coating that we discussed. In those locations, you can have a pipeline that was meant to last 50 years suddenly start corroding and maybe only have a lifespan of 5 years. So it can be fairly traumatic and something that pipeline owners will often monitor. One thing we can look at is the AC current density, which is often described as the amps per meter squared. And what the standards typically dictate is around 30 amps per meter squared. That's where we can start to see some AC corrosion concerns occurring. So that'll be one of the criteria that we look at from an AC interference study with pipelines. During fault conditions, we have, again, a personal safety aspect. For North America, we'd be primarily looking at the touch voltage criteria from IEEE standard 80, as well as the step voltage criteria from that. This is analogous to the EN 50522 or the IEC standards related to touch voltages during fault conditions. Really what we're looking at is the voltage difference between a metallic component that may have induced conducted voltage on it, a person's hand to their feet, and that voltage difference creates that touch voltage hazard. Again, we have concerns about the pipeline integrity itself. This can be the coating stress, so the dielectric strength of that coating that you have on the pipeline may be insufficient if you have 3,000 volts of in your soil and the pipeline itself is maybe a couple volts. That may be sufficient that you can puncture the pipeline coating. And you can actually have direct arcing in instances where you may have some exposed metal of that pipeline, kind of referring back to the previous discussion about the ionization of the soil, and kind of depends on the proximity of that transmission line to the pipeline. Now I want to get into railroads as well, because we do want to touch on AC interference related to railroads. So rails, we see the metallic component that we can induce upon. This is the rail itself, and it's important to understand that rails may have track signaling on them, meaning that the control and operation of these trains can be automatically controlled through signaling on the rails. Often more modern signaling is used that can be more robust against AC interference, but there's a lot of rail systems that use track signaling to indicate how fast a train is coming to any sort of road crossing, and that can be relatively easily affected by small amounts of induced voltages on those rails. With that track signaling, train operators need to have a sufficient ballast or sufficient resistance between their rails so that they can actually carry that track signal. And this is often described as OMK foot or OMK meter. So that will be one characteristics that you would capture in XGSA FD when you're studying these types of rails near transmission lines. And again, we can have control houses that are holding all of our infrastructure, and that can have either touch voltage hazards to them or equipment hazards. So we'll go over the steady state operation concerns for railroads. That's going to primarily be, again, the touch voltage hazard during steady state. Usually railroads, they tend to use a 50 volt limit in North America, referring back to the OSHA standards. We have the signal misoperation that could occur. Essentially, if you have something as minimal as 5 volts from one rail to another, that can be enough such that the grade crossing predictors can't determine if there's a train coming, and then they may drop this crossing arm when there is no train. And that can lead to the public losing trust in the accuracy of the rail system, and then you have people driving around the train and or driving around the tracks and not really paying attention to the train anymore, which is another safety concern. During faulted states, we have similar type of concerns that we talked about with the pipeline. Personnel safety hazards, often referencing IEEE standard 80 in North America. The ARIMA standard has a 430 or 650 volt limit. Again, kind of going back towards the calculation criteria from IEEE 80 for how much voltage somebody can withstand for that short duration of a fault. We also have signaling equipment limits, so they have their own surge protective devices, and they may not be able to withstand the energy or the current and duration that a fault would carry or conduct onto the rails and onto that signaling equipment. So those are the concerns that we may have associated with railroad hazards, for instance. So I'm going to switch over to XGSAFD modeling in just a minute, but what we try to do is we're going to gather information from multiple sources and multiple industries. So we have our transmission line side, where they may provide a plan profile, phasing arrangement, the load current and fault information. On our recipient side, that could be the pipeline or the railroad, we can have the pipeline alignment, the appurtenances associated with that, those test stations, test valves, or the valves, that coating material and its properties. On the rail, again, we'll have an alignment that will give us information about the signaling equipment. Different equipment may have different susceptibility to rail voltages, and it's important to have an understanding of the ballast resistivity as well, because that will provide an insulating property to those metallic rails and help increase the overall induced voltages from the shared corridor. So the overall modeling process essentially is you develop your base model in XGSAFD, do your steady state and faulted state analyses. You may need to consider some recipient operation practices, such as railroad, for instance. They may be able to operate under one device's failure. So that could be an insulating joint is failing, creating a much greater difference in the exposure length of one rail to another. And because there's a shared corridor concern, you could have overall greater induced voltages and greater rail-to-rail voltages. So at this time, I'm going to pull off of the PowerPoint and switch into our modeling software. And actually, before we get into the modeling software, for those of you that haven't seen these pipeline arrangements or plan and profiles from transmission lines, here I have a PDF of a pipeline arrangement drawing or stationing drawing. And what you typically would see is some sort of satellite imagery, and this gives us more of a top-down view of the pipeline's path and location. And there's multiple other lines here, but if we scroll down, we can see the stationing that gives us information about the depth of that pipeline, some of the locations of various appurtenances, if there is some sort of drilling. And if you are drilling your pipeline, there may be some sort of backfill material or mud that they're using in order to place that pipe. This gives us information about the length of the pipeline as well. So we can see this is the stationing 50 plus 00. That's 5,000 feet, 40,000 feet, or 4,000 feet, 5,000 feet, 3,000 feet. And then on our legend, we can see some of the other entities that may be related to this pipeline's installation, such as power lines, which is going to be our main concern. So scrolling back up to our satellite imagery, we can see our pipe alignment drawing. And then next to this, we see this P and line indicating where the power line's path may be. So this is one of the data points you may receive from a pipeline utility. On the transmission line side, or the transmission owners, they often give a plane and profile. Again, we start off with a kind of top-down view from satellite imagery showing the location of towers, the path of the transmission line, and if we scroll down, we'll see similar type of information giving the separation distance from one transmission tower to another, but we also get information about the elevation or heights of each of our phase conductors, as well as the maximum sag characteristics that we may see from this. So here it's a little blurry, but we go from an attachment point that's at an elevation of 1,510 feet down to an elevation of 1,480 feet. So it's about 50 feet in sag from our attachment point to the lowest point of our phase conductors. So taking this information, we can use another type of CAD tool. So here I have MicroStation, for instance, where you can just take those plan profiles, place them into the drawing, and then after scaling, we can start drafting over a rough path to illustrate where our pipeline is. And we do a similar type of operation in following the pipeline path. So we would essentially follow the lines that are illustrated there to create our path for both our pipeline and our power line. What I want to do is there's other tools that can pull in directly from a Google Earth type of image. So let me pull open my other drawing here. I'll close this one. And I already have this somewhat prepared. I want to show the background of this. So here we have Google Earth synced into the software. And if I zoom in, this white line, what I've done is I'm following the path of one of my phase conductors, and this is giving me a approximate location of my phases. Obviously, a lot of this information is easier to acquire if you can get a direct export from the PLS CAD model that may be used to develop the transmission line or the shape files related to the pipeline, and then put those into XGSA FD. You can import them individually. If you don't, these are kind of typical processes I end up using because it may be challenging to get the information from either utility. So this process, really all that we do is we're following the phase conductor, and I simply select where I see this on my satellite image, and I make a line for each point that I see the tower. And the reason I do that is that when I import this into XGSA FD, each one of these lines is going to be interpreted as a new segment, and that allows me to give an accurate sag characteristic when I pull that in for our transmission line side. And here we have our pipeline, which again, we're just going to follow any one of our stationing points to create our path of the pipeline. And then once we export this to a DXF, that's something that we can import into XGS Lab. So here we have XGS Lab as you would start up, and I've already selected XGSA FD, and I need to set my standard to IEEE standard 80 for my touch voltage hazards under fault conditions. I'll set my frequency to 60 Hertz, and I will assume just 100 ohm meter resistivity for now. And I need to point to my DXF that we created. And I'm just going to pull in the layers this zero layer, that's that white line that we were looking at. This is my phase conductor, and I'll call that a line, give this overhead characteristics of tutorial 1, and give it a unique tag name. And I do need to elevate the phase conductors, but we'll do that once we've imported. So next I'm going to import my pipeline. I'll assign this as electrode 2, and I will specify the pipe characteristics by going to my description. And this one I know that's already at a depth of 3 feet, so I'm going to shift my imported line in from the DXF in the XJS AFD to be 3 feet into the earth. So when I import this, what we'll have is exactly what we saw on our CAD drawing. So we have our list of conductors, and now we have our pipeline illustrated here and our transmission line illustrated here. And the first thing I want to do is I want to start creating my other 3 phases. And again, what my goal here is to kind of show some optimal ways to develop your model. So I'm going to offset and then shift this 23 feet off of my phase A, because that's the separation distance from one phase to another. And if I zoom in here, you can see I now have 2 phase conductors, but both of them are described as phase A, and that's not ideal. So what I will do is I go to my list view, and I'm going to give myself a little better tag naming scheme. So right here, we'll just select the second set of phase A, because these conductors were all drafted after my pipeline, so they appear later on in my list. And this allows me to select that conductor, and now I can relatively confidently say that that's going to be my phase B. And while I'm here, I will switch this over to a source, and this is how I will energize my model with my steady state load current. So if this is a 230 kV line, for instance, that will be represented with the 230 divided by square root of 3. So we have 132,790 volts. And we'll put this at 120 degrees. So there's 1,000 amps of steady state load for our maximum steady state load, and we'll apply that. And if I go back to my draw view, now, if I zoom in a little bit, we can see I have a phase A that disappears once I select my filters, and a phase B. So now I have some independent selection for each of these, which is convenient because now I can, again, go to my conductor editor. Phase A needs to be energized as a source, and I will use that same criteria because we're using steady state. I'm just going to have this at a 0-degree angle. Then we have our 2 phases. We need our third phase C. And in order to create a kind of efficient process like we did for selection, I'm going to create what I'll call this a flag conductor. This is just for my list view so that I can easily see any of my new conductors that I'm about to offset. So I have this conductor, it doesn't matter where I place it, but now I can go back to my phase B. And again, what we're doing is just playing around with our draw view and our list view to create a pretty efficient workflow for creating these. So I'm offsetting 23 feet like I did a second ago with the phase A to phase B. And then in my list, you can see my flag conductor here, and then this is my new conductors that I've just offset, and I will go to my conductor editor to make these phase C with a negative 120 degree. So if I go to my draw view here, allow all of my tags, I'll delete this. There we go. So now we have the pipeline and my transmission line represented here. I do need to shift my transmission line up into the air, but I also need to consider that catenary curve or that sag characteristic that we looked at. So I will place this. We'll use our catenary curve process. So we'll say this is starting at 85 feet as its elevation, goes out 500 feet, sags to 45 feet, then increases to 1,000 feet in its path, and then we'll bring that back up to 85-foot elevation. So here we get the catenary curve characteristic, and I'll go ahead and select this A parameter. So going to my draw view, we'll zoom in again at these, and all of my phase conductors are right at the Earth's surface, which isn't ideal, and they don't consider that catenary curve. So I will select just phase A, B, and C, go to my conductor editors, and all of these are going to be edited in mass. So I want to elevate these to be negative 85 feet into the air and put in a catenary curve. And so if I zoom in, what we'll see now is we actually have this catenary curve approximated for this system. And now we have our kind of base model for doing steady state analysis and relatively quickly developed. What I want to do is highlight that when we have a transmission line next to a pipeline or some other entity, we often want to incorporate simulate this infinite length as if this pipeline were to go on indefinitely. And the reason you do that is to avoid end effects. And incorporating that in XGSA FD is pretty convenient. There's a little power tool that we're just entering. And now I can run this model and determine the induced voltage on that pipeline for personnel safety hazards, as well as the possible AC corrosion risk. And this just take a few seconds. Once I have that, we can go to our distribution, and I will look at the voltage that is induced on our pipeline. And we can see this in my 1D view. I need to switch this to consecutive so the path is one conductor after another, and we can create this profile. And we can see relatively low voltages are induced in this particular corridor, only 5 volts. And if I go to my view 2D, you can see this illustration of this point right here is where we have that maximum induced voltage. Even though it's only 5 volts, that might be sufficient for concern of leakage current or accelerated AC corrosion. So we'll make a 1 centimeter squared holiday. That's going to be 0.39 inches approximately. Then we'll again do this 1D plot to make the path along there. And if there were issues, we'll make sure this shows up. You could illustrate your limits using the limits 1 and limits 2, since we don't have we can illustrate here increasing my maximum value that we are well below this 30 amps per meter squared for that pipeline. And this is kind of the initial starting point for developing a base model. You kind of have multiple ways in order to get a model into the software, and then you want to get it analyzed, at least for the steady state. And I want to switch gears to show a little bit about a railroad in the next 5 or 10 minutes before we do some fault analysis. So I have something similar to what we create for our tutorial documents. So if you haven't seen it, there's an XGSA FD tutorial for AC interference, and it kind of steps you through that analysis process. really, again, importing from a system. And if you can, it is much more convenient to create a pretty robust drawing in your CAD program that you can import the various conductors from, such as the XGS-AFD tutorial. We have this transmission line. You can see right here with all three phases, overhead shield wire, and a pipeline next to it. So if you can create something like that in your CAD program, that's pretty convenient for importing into XGS Lab. And again, highlights XGS Lab is a pretty integrated tool in order to take in information from other sources and export that out. So what we have is now a railroad model that we're going to look at for steady state induced voltages. And the railroad differs from the pipeline in that instead of just one conductor, we now have two conductors along this path. So if I click on this, we can see on my conductor editor, I drop down to my properties. This is my rail. And that property is assigned through my conductor libraries. And this rail characteristic, going to conductor editor, has a steel metal, and it's covered with a rail ballast. And the rail ballast has to be approximated in the software. And you can get an estimate of that by taking the characteristics that I have modeled here and then just doing a sample model, for instance, just 1,000 feet or 1,000 meters of that rail. And you can inject current on one of the rails in the positive domain, inject, well, I'll show you here. So here would be my rail ballast modeling. So if I go to my draw view, what we can see is, if I zoom in, I have two rails using the same characteristics that we have in my other model. So that's the rail description. These are separated by 4.5 feet approximately. That's typical for rail separation in North America. And this rail is energized with 1 amp at the starting point, while this rail is energized with -1 amp. So that's essentially the current going in and out of our model. And because my model is, we'll measure it, (3,268 feet), that's approximately 1 kilometer. If I run this model and look at the voltages on that, one of these rails has a voltage of 2.46 volts. The other has 2.46 volts, but in the opposite angle. So you have a total difference of 5 volts between rail to rail. So that would tell me that I have a 5 ohm K-meter ballast that I've modeled in this software. So that's one way to verify that your ballast is properly considered with your modeling mechanism. I think I'm going to run a little tight on time here, so I do want to show with a rail system what we're looking at. So I will go to expand my view. I've already ran this model, and again, steady state model, and we look at the distribution, and I want to see the voltage that's induced on the rails, for instance. We can view this in 1D or 2D view. You can see that we have approximately 48 volts that's induced on the rail, but that's just one aspect of this. We need to understand the difference between rail 1 and rail 2. So we can do that relatively conveniently using this potential difference value. And if we use a reach distance of 5 feet so that it looks from rail 1 to rail 2, we set my tag filter to be rail 1 and rail 2. Now I can see in XGS-AFD the differences in my rail-to-rail voltages. And we can see in this little bit flatter area, we range from 7 to 12 volts. And then we have these peaks right at this point. And we'll also see this is rail 1's information and this is rail 2. So we kind of have that duplicated, but gives us kind of an automated format to read. If we go to my 2D view, those peaks are going to be generated right where we have our insulating joint. And I'll zoom in on that. So right at this insulating joint, at this point, where we've put in a transverse impedance, or longitudinal impedance, apologies, that is where we have those peaks that we saw in this rail-to-rail voltage reported. And this could correspond to somebody reaching on one half of the rail and the other half of the rail across that insulating joint. The other parts within, what we're looking at is the voltage difference between rail 1 and rail 2. And we can look at those results. I'm going to switch from our potential difference, and we'll look at our potential of the rails specifically. Since I'm zoomed in, you can see we have this peak voltage coming over. If I click on my conductor right there, I can see I get a voltage of about 39.87 volts. And in the adjacent rail, we have a similar, there's a little bit of a phase difference between one rail and the other. So that's going to relate to the, or vector difference between one rail and the other. So that's going to correlate to a rail-to-rail voltages that can cause some misoperation in that rail-to-rail signaling, or the track signaling. And Danielle, I know you're the timekeeper, and I might be running out of time. I was going to show one more thing related to faults.
Well, do not worry, David. We are still a bit fast on the agenda. So if you still have some detail to show, take your time and go on. You still have, well, maximum 15 minutes, but I think they will more than enough.
Okay, perfect. I have this problem of having more content than time, so
no worries.
Appreciate that. So we kind of looked at steady state for a pipeline, steady state for a railroad, and kind of efficient ways to get the information out from that software and view it. Kind of get the information in and information out from the software. Next, we want to look at a fault condition. So here we have a fault scenario. I'm pretty much using the tutorial as the basis because it has a nice long path where we are parallel between the pipeline and the transmission line. Again, I've switched this model back to be a pipeline in this particular model. And what I'm concerned about is a fault through the corridor, which is simply if I were to take my phase conductor, so zoom in right here, and we just change that source from 1,500 or 1,000 amps to 20,000 amps, well, then we can account for the induced voltages that occur from that transmission line phase conductor to that pipeline that's magnetically induced, electromagnetically induced. We also have a concern of faults happening for each of the towers in this corridor. And one of the advantages of Scheduler is that it allows me to put a reference in at each one of these points. And if I kind of go along here, you can see I've placed a reference on each one of my approximations of my tower model. So that's just a simple linear conductor, almost like a monopole. So it's a relatively thick steel pole that goes into the earth, that's embedded into the earth. And that is what I have flagged as a reference. The convenient thing is that I can take each one of these flags, these references, this P1, P3, P2, and create a scheduler based off of that. Save that. So I'll go to scheduler, and I simply just add in my base fault model. So I'll point to that base fault model, right click to go to the parameter editor, add in my energization, and I'll call out my references. So P1, vertical bar between P2, vertical bar P3, and then P4. Then I'll put in that 20,000 amps that we saw as the fault current. And then I check this, and that parameter is ready to run in scheduler. Once I hit confirm parameters, then I'm ready to run the model. And we'll do a little bit of kind of that cooking show thing where this is the setup of the analysis. Once this runs, each one of those takes maybe a minute or two. I get several outputs. One of them corresponding to each of my parameters. So if I look at P1, this XGSA FD tutorial fault P1, what we'll see is the fault of 20,000 amps is now asserted into my reference point P1. So we'll go to my draw. And you can see here, just through scheduler, that's how this fault is energized right there. And when we look at the analysis, because this was previously ran, I'll go ahead and plot the Earth's surface potentials here. We'll look at the Earth's surface potentials, and we can see a significant voltage or ground potential rise at the tower location, and we'll be concerned about touch voltages to this pipeline. So we can change our filter to look at just touches to that pipeline. I might limit my reach to, we'll say 4 feet, that's fine. So we'll only get results around that pipeline. The yellow is indicating that I'm exceeding my compliance limits. And then I'll go to my non-filtered view, and we can see I have a touch voltages that are kind of lowest next to this pole because we have the Earth's surface potential here. That's approximately 3,100 volts. If we look at the pipeline voltage in that area, I suspect we'll see the pipeline voltage is pretty high at this location and starts to decrease. So you have the pipeline voltage maintains a higher voltage, we'll see. So right there, we can see the pipeline voltage itself is 3,991 volts. And it kind of maintains that voltage because of that coding. So we have a point next to the transmission line where we're elevating the soil voltage due to the conduction from that tower that is actually reducing the voltage difference between this pipeline and the soil. And that's, of course, going to correlate to our coding stress as well. So we can look at this and say, all right, well, our voltage difference between the soil and that pipe itself is somewhere in the range of 3,000 to 400 volts, depending on what part of that pipeline you look at. And often when you have a tower or transmission line with overhead phase conductors, you'll have a fault maybe at one tower, but the adjacent few towers will actually see a ground potential rise going down that corridor. So that's why we'll look at multiple faults. And all of these things you can develop exports from these elements, and then you can import them all into a database in Excel for plotting them all together. And I will kind of pause here to give people a moment to ask questions. I know I tried to cover a lot of ground, primarily in illustrating how you take the beginning information, create the initial base model, transform that into your steady state analysis, and then into your fault analysis for both pipelines and railroads.
Well, thank you very much, David. Your contribution was absolutely great. And well, If there are some questions, please prepare them, because we already have two of them. So I would like to answer them for all of you. First of all, they are both from Mr. Nazemi Mohammed from Amprion. And basically, he argues that the offset feature about drawing does not work properly in every scenario. I confirm this. Let's say that it is part of the limits of the raster graphical output we have. And it will be overcome in the near future with the proper CAD we are going to implement inside the software. That will be a really breakthrough. I suggest you to stay tuned in our channel, let's say, because for sure we will have great news on this side within this year. And well, let's say also he mentions about working with the coordinates. Let's say that the software, I can also maybe share my screen very quickly just to make everyone aware of this. Okay, if we select one project, let's say that if you go on the list of the conductor, you can export or import this list, and by using you export a list in XML format, and by using Excel, you can work on that, and then you can also edit and create new models by starting by always the same list of values. There is one thing more about the scheduling. Let's say that the scheduler that I presented in the very first part of this webinar is something that is at the beginning in our programs. That is to say that we have a quite short list of parameters that can be set. So we can switch on or switch off tags. We can set energization. We can set frequencies. We would like to set soils in the future. We would like to add some other parameters. Also, in multi-layer soils, we have to think about that. And moreover, we would like also to build a collector of the results in the scheduler in order to have a real parametrical analysis that can analyze the results that this tool generates and put them together in a analyzer that is able to appreciate and to make valuable those results. So these are the very first questions, and I hope that these answers were sufficient. There is another question from Imre Tannemat.
Yeah, that question is, do you also consider asymmetry of load currents for calculation of induced voltages? I've personally not done that for the analysis for kind of high voltage AC interference. It is I've seen a few papers on it, and it typically would affect lower voltages more significantly. And the problem is that you can also get those third harmonics that can also induce higher voltages at lower or with less exposure lengths. So it's certainly something that is a viable concern. One thing with harmonics side of it that kind of varies into it, third harmonics especially, on pipelines, you tend to have more resilience to that third harmonic because it doesn't create as much of an AC corrosion concern. And this is kind of a steady state concern. On the rail side of things, you can have a much bigger problem because the track rail signaling could operate at 200 hertz, which can be much closer to that 180 that you're third harmonic would be at. So I think it's a valid concern. It's not something that's typically looked at in the industry, but if you have a system and an environment where that is an issue, it's easy enough to create that offset in XGS-AFT. And one thing I wanted to show too is if other questions are pausing. So with that scheduler tool, it creates these element files. So each one of these you can copy out. And what I will often do is put these into like a co-location file. And oh, sorry. Each one needs to have its own unique name first off. But if you had its own unique name, then you could put all those files into the same folder, and then that's something that you can pull in using Excel to simply just point the software to a folder, and then it can import all of those CSVs, and then you can create your same plots that we did with our model here. So instead of plotting it in XGS-AFD, you can have all of your multiple scenarios for faults plotted in the same view, we'll call it. So that's another methodology for essentially creating this, we'll call it linear voltage graph. So really, in conclusion of this type of study, is that AC interference is, as pointed out, the way that you kind of create your model depends on the inputs that you're given. So what that plant profile may look like, what the pipeline information is, and you have to customize each model according to that specific scenario. And then you can evaluate the personnel safety hazards or equipment damage that could occur for various types of recipients. And with the more efficient input and output process, you can do these studies relatively quickly with XGS-AFD. And really depends on what your typical information that you typically receive and what your clients typically want to see as the output.